Welcome to the Deep Dive. Today we're digging into something pretty crucial in engineering and business processes, making sure things actually run the way they're supposed to.
Exactly. It sounds simple, but checking if what really happens, the event logs, actually matches up with the design process model. That's a big deal for improvement.
And it gets complicated fast,
Yeah.
especially figuring out the best match, the optimal alignment between the log and the model. There are just so many possibilities.
Right. The computational costs can explode. Existing methods often just, bog down. They don't scale well.
Which brings us to the paper we're looking at. It introduces something called DeclareAligner. It's a new algorithm, isn't it? Using a search.
That's the core idea, yes. A is a well-known AI search technique, and they've cleverly adapted it for these flexible declarative process models. It promises much better efficiency.
Okay, so what's the key advantage? How does it achieve this?
Well, there are a few things. It focuses specifically on fixing the constraint violations, the mismatches. It uses a smart, tailored heuristic, a kind of educated guess, to guide the search. And it employs early pruning to cut off dead ends, plus some streamlining, like pre-processing and grouping fixes together, makes the whole thing faster.
And they tested this thoroughly.
Oh yeah, huge data set, synthetic, real-world problems. The paper shows DeclareAligner really outperforming older methods, significantly faster, fewer timeouts.
Interesting. So for this deep dive, we really want to unpack how DeclareAligner pulls this off and, why it's a significant step for process mining.
Let's do it. So fundamentally, the paper tackles efficient, optimal conformance checking. That's the goal.
Optimal alignment, meaning the alignment with the minimum cost of deviations, like the fewest changes needed to make the log fit the model.
Precisely. Minimal cost sequence of deviations.
Huh.
It finds the most economical way to explain the differences between the observed log trace and the allowed behavior in the model. Super important for actually diagnosing problems.
And this is specifically for declarative models you mentioned. Why focus on those? What's different about them?
Right. Declarative models, like ones using the declare language, they're all about flexibility. Instead of mapping out every single step, like A, then B, then C.
Like a traditional flowchart, maybe.
Exactly. Instead of that, they define constraints. Rules like activity X must eventually be followed by activity Y, or activity Z can never happen after activity W.
So they allow for more variation as long as the rules aren't broken.
Precisely. Which is great for complex, real-world processes where things aren't always rigid. But that flexibility makes conformance checking way harder.
Yeah.
Because any sequence is okay as long as it doesn't violate a rule.
So the space of possible correct executions is massive.
Exactly. Finding the optimal alignment in that huge space is computationally very, very expensive for older techniques. Even ones designed for declarative models often hit a wall.
So DeclareAligner is aiming squarely at that scalability problem.
That's the core contribution, yeah.
Yeah.
Making optimal alignment practical for these flexible declarative models.
Okay, maybe some context would help. How did we get here? What's the background in process mining leading up to this?
Sure. So process mining itself covers a few areas. Discovering processes from data, checking conformance, which is our focus here, and enhancing models.
Conformance checking being the comparison part. Log versus model.
Right. And as companies got more systems logging everything, the need to verify processes grew. Alignments came about as a way to get a detailed step-by-step comparison, not just a pass-fail.
And optimal alignments add that cost dimension we talked about, finding the best explanation for the differences.
Yep. Penalties for mismatches, like an extra step in the log or a required step missing. Find the alignment with the lowest penalty score.
You mentioned traditional models becoming spaghetti models sometimes.
Yeah. For really complex processes, trying to draw every path with an imperative model, it gets messy fast. Declarative models were a response to that define the rules, not every single path. Declare became a key language for that.
But that flexibility created the conformance challenge.
It did. Early declarative conformance tools might just say constraint violated. Not super helpful. Later tools got better, identifying which constraints failed.
But still not giving that optimal alignment, that minimal set of changes.
Generally, no. Or the methods that could find optimal alignments, maybe using things like finite state automata conversions, often choked on the complexity. They just weren't efficient enough for many real cases.
And that's the gap DeclareAligner fills, using a search, which had already shown promise for imperative models.
Exactly. Adapting and optimizing A specifically for the quirks of declarative models.
Okay, let's get into the algorithm itself then. DeclareAligner. You mentioned a search. It explores states, right? What constitutes a state here?
Right. A state and DeclareAligner search isn't just a point in the process, it bundles up several things. The alignment costs accumulated so far, the heuristic estimate of the remaining cost.
The educated guess part?
Yep. Also, something called an LT graph. Think of it as a dynamic representation of the activity dependencies found so far in the alignment. Crucially, it also tracks which constraints are currently violated and which specific violation the algorithm is actively trying to fix next.
And the starting state is basically just the raw input trace.
Pretty much. The initial state represents the event log trace, often pre-processed a bit, loaded into that LT graph structure with an initial cost of 0 and a list of any constraints it violates right off the bat.
How does it move between states? How does it explore?
It generates neighboring states by applying fixes to the constraint violation it's currently focused on. Each fix represents a potential change to the LT graph to satisfy that constraint.
And how does it choose which violation to fix or which fix to apply if there are options?
It's quite smart about it. It prioritizes exploring fixes based on their potential cost. Usually it looks at the fixes with the highest cost first.
Highest cost? That seems counterintuitive. Wouldn't you want the cheapest fix?
It seems that way, but the idea is that high-cost fixes, like inserting or deleting an entire activity, often have broader consequences. Addressing those big deviations early can prune the search space more effectively and prevent cascading issues down the line.
Ah, okay. Tackle the big problems first. What if multiple violations have fixes with similar costs?
They have tie-breaking rules for that. It depends on the constraint type. For forward-looking ones like response, A must be followed by B, it often prioritizes fixing the last violation instance. For backward ones like precedence, A must come before B, it might focus on the first instance. Negative constraints have their own logic too.
You keep mentioning fixes. What kind of changes are we talking about? What can it actually do to the LT graph?
Several things. The most significant, cost-wise, are inserting a node representing an activity from the model that wasn't in the log, or removing a node, an activity log not allowed by the model at that point. These are the costly model moves or log moves.
Okay.
Then there are cost-free fixes, like adding an arc to enforce precedence, setting specific start end nodes for a process fragment, handling choices between activities, or merging splitting chains of directly connected activities. These adjust the structure to satisfy constraints without implying a mismatch between log and model.
Got it. So the algorithm explores these fixes, guided by cost and priorities. How does the heuristic function fit in again? How does it estimate that remaining cost?
The heuristic is vital for efficiency. It estimates the minimum additional cost needed to get from the current state to a goal state where all constraints are satisfied.
How does it calculate that estimate?
It looks at each currently violated constraint activation individually and determines the cheapest set of actions, like inserting nodes, required just to fix that specific violation. Then it uses a variant of Dijkstra's algorithm to combine these minimum costs optimistically, meaning it assumes fixes might be shared across multiple violations where possible. This helps prevent overestimating the remaining cost, which is crucial for A to work well. It needs an admissible heuristic one that never overestimates.
Okay, so A finds a path to a goal state, one with no violations. How do we get the actual alignment sequence from that?
Once a goal state is reached, the final LT graph in that state represents a valid constraint-satisfying sequence. The algorithm performs a topological sort on this graph.
Which gives a linear order of activities respecting all the dependencies.
Exactly. Then it essentially walks through this sorted graph sequence and the original event log trace simultaneously. If an activity in the graph matches the trace, that's a synchronous move, a match. If an activity is in the sorted graph, but not at the current position in the trace, because it was inserted as a fix, that's a model move. If an activity is in the trace but not the graph at that point, because it was effectively removed or skipped, that's a log move. This step-by-step comparison is the optimal alignment.
That makes sense. A methodical reconstruction. Now, the paper stressed optimizations. Let's revisit those. First step was early pruning.
Right. Early pruning is about cutting off branches of the search that are guaranteed dead ends. Huge efficiency gain.
How does it spot a dead end?
Two main ways. One, if a state has a violated constraint activation for which there are literally no possible fix actions defined. If you can't fix it, you can't reach a goal state from here. Prune. Two, if applying a potential fix would create a cycle in the LT graph. A cycle means contradictory ordering requirements, like A must come before B and B must come before A. That's impossible in a valid process execution. So any fix that creates a cycle is discarded, pruning that path.
Smart. Stops wasting time. What about the second optimization, constraint preprocessing?
This one targets specific constraint types, primarily chain constraints.
Yeah.
Like A must be immediately followed by B, then C, if the initial event log trace already contains sequences that satisfy these chains.
Like you see A, then B, then C right there in the data.
Exactly. DeclareAligner merges those activities in the initial LT graph setup. So instead of 3 separate nodes for A, B, C, it might create a single combined representation for that chain.
Why? What's the benefit?
It reduces the initial complexity. The algorithm doesn't have to rediscover and enforce those already satisfied sequences through multiple search steps. It bakes them in from the start. Fewer states to explore.
And the third one, grouped fixes. How does grouping help?
This tackles cases where fixing one violation might logically require several actions. Think of an existing constraint. Activity X must occur at least 3 times.
Okay.
If the log only has X once, you need to insert it twice more. Instead of having 2 separate search steps, one for each insertion, DeclareAligner can bundle these into a single grouped fix, insert X twice.
Ah, so it makes bigger, more meaningful steps in the search.
Precisely. It avoids exploring lots of intermediate, partially fixed states, collapsing multiple related actions into one transition. Again, fewer states, faster search.
These optimizations sound like they'd make a real difference. What did the evaluations show? How big was the impact?
It was significant. They did an ablation study, turning each optimization off one by one. Early pruning had the biggest single impact, something like an 83% reduction in time and nearly 90% fewer states explored on average.
Yeah.
Huge. Pre-processing and group fixes also showed substantial gains, reducing time and, crucially, the number of problems that timed out before finding a solution. Combining all 3 gave the best results, naturally, like a 92% time reduction overall compared to the baseline with no optimizations.
That's dramatic. And how did the fully optimized DeclareAligner stack up against other existing tools?
It came out clearly on top. Compared to other declarative aligners like DeclarePlayer and approaches using AI planning like Planner BA, DeclareAligner had significantly lower average runtimes and far fewer timeouts across the board.
Did it solve problems the others couldn't?
Yes, it successfully aligned thousands of pairs within the time limit, significantly more than the competitors. I think it solved over 200 problems that none of the others could handle within 5 minutes.
So statistically significant improvement.
Definitely. They ran Friedman and Holm tests, standard statistical comparisons, confirming DeclareAligner's superior performance. The numbers were compelling, like being able to align 90% of the test cases in under 3.5 seconds.
Yeah.
That's a big step up.
So translating this back to the real world, what does this mean for organizations actually trying to use declarative process models?
It means practical, scalable conformance checking is much more feasible now, even for large, complex logs and models. Organizations can get faster, more reliable feedback on how their processes are actually running compared to how they should be running.
Which enables what? Faster improvement cycles?
Exactly. Faster diagnosis of why deviations are happening. Better understanding of the root causes of inefficiency or non-compliance. It provides a much more solid foundation for process analysis and targeted improvement efforts.
Being able to pinpoint those minimal cost deviations helps focus resources too, presumably.
Absolutely. Instead of guessing, you get a clear picture of the most economic set of differences. That helps prioritize where to intervene or allocate resources for fixing process issues, or maybe even refining the model itself.
This definitely sounds like a solid piece of engineering addressing a real pain point. Okay, let's shift gears slightly to our novel notions segment. Based on DeclareAligner, any speculative research ideas or extensions spring to mind?
Well, one thing that struck me was the effectiveness of the tailored heuristic. It's designed based on the constraint types. It makes me wonder, could the heuristic become adaptive?
Adaptive, how so?
Imagine if, during the search, the algorithm started noticing patterns in the violations it's encountering. Maybe certain types of constraint violations tend to cluster together, or maybe fixing one type often leads to another specific type popping up.
Okay.
Could the algorithm learn from these patterns in the current trace? It's analyzing and dynamically adjusts its heuristic. For instance, if it keeps seeing a pattern suggesting a resource bottleneck is causing delays that violate multiple timing constraints, maybe it could tweak the heuristic to more heavily penalized fixes that don't address that potential bottleneck.
So the heuristic tunes itself based on the specific problems it's seeing in this particular alignment task. Like it develops intuition for the specific process instance.
Sort of, yeah. It's building on the tailored heuristic idea, but making it dynamic, integrating maybe some lightweight machine learning or pattern detection during the alignment process itself.
That's a cool idea. Connects back to the AI roots of A.
Right. The obvious support is that a heuristic, more finely tuned to the immediate problem, should guide the search even better. The less obvious part might be uncovering complex interactions, how fixing one violation nonlinearly affects others, and maybe the adaptive heuristic could start to model those interdependencies better than a static one.
What would be the potential impact if that worked?
Potentially even faster alignments, especially for processes with really specific or recurring deviation patterns, maybe even enabling near real-time conformance monitoring in some dynamic environments where the nature of problems shifts over time.
What's the catch? What's the tricky part or the commonly overlooked aspect?
Well, the main risk is complexity. Making the heuristic adaptive adds overhead. You need to analyze patterns, update the heuristic function. Does that computation cost more than it saves in search time? That's the balance.
Right. You don't want the adaptation itself to become the bottleneck.
Exactly. And there's the risk of overfitting the heuristic to one specific log or time period, making it less effective if the process behavior changes significantly later. Ensuring robustness would be key.
Makes sense. Fascinating direction to think about, though. And just a reminder, folks, these novel notions are purely speculative, food for thought.
Absolutely. Just extending the ideas from the great work in the paper.
Well, this has been a really productive deep dive. DeclareAligner seems like a genuinely significant improvement for anyone working with declarative process models and conformance checking.
I agree. It tackles a hard computational problem with a well-engineered solution, leveraging classic AI search techniques in a smart way. It really pushes the boundary of what's practical in process analysis.
It empowers analysts with faster, more scalable tools to really understand and improve those complex workflows.
Definitely. Having efficient optimal alignment is a key enabler for deeper insights and more effective process improvement initiatives.
For listeners wanting the full technical breakdown and evaluation results, we'll have the link to the paper itself in our show notes.
It's worth a read if you're in this space or just interested in the application of AI search to real-world process problems.
And to leave you with a final thought, as AI continues to evolve, what other parts of process analysis and improvement might see similar breakthroughs? Where else can intelligent algorithms help us better understand and optimize the complex systems we relied on every day? Something to ponder. Thanks for joining us on the Deep Dive.